Okay, let's go ahead and get started today with today's lecture. Today we're going to be talking about a couple of things that are going to end up being important to us later on. This is Class 7, Systems Programming. So today we're going to be talking about pointers and operators. So let's go ahead and get started. So operators, like in any other programming language, let you calculate things and they produce some value from another value. So operators would be like arithmetic operators, like plus, minus, multiply, divide. But then as we're going to see, there's some other operators that we're going to see as well. And some of them are going to look different than you're used to if you're used to a language like Python, for example. So C has a fairly rich set of operators, but they're designed, remember C is kind of this mid-level language that was designed to be close to the hardware on the machine. So that means the operators closely mirror the instructions they're in the instruction set of most microprocessors. And that also means that there's going to be a notable operator that's missing, and we'll see that here in a second. All right, so before we get into the operators, though, I want to look at something. We're going to introduce this concept of what's called a pointer, and that's going to be important to some of the operators that we see here. Now, what's a pointer? Well, to understand that, it's important to note that every variable, and really not just variables, but anything that's in memory, or every piece of data, every piece of code, the instructions that the processor runs, the data that those instructions then use, all of that is stored in memory. If you remember back to really classes 1 and 2 and part of 3, we had that model of the computer that had like this memory, and then we had a processor, and the processor could access the data that's stored in those memory boxes. So that means that every piece of data has some address associated with it to tell apart this memory location from this one, from this one. So each of those pieces of data lives in that memory at some different address. So that means that every variable is storing the data that it's storing in memory at some particular location or some address. And C, being a systems programming language, can give us access to the address of any variable. And as we'll see later on in the course, not just any variable, but any piece of data that's in the program. All right, so to access the address of a variable, we use this operator, the Ampersand Operator, which is considered to be the address of operator. And that address of operator results in the address of whatever variable that follows that. So for example here, ampersand variable, that means address of whatever this variable is. If I had a variable I could put ampersand I, which when I would read that code, I'd read that as the address of I. So in other words, what is the address of where that variable is being stored, the data in that variable is being stored in memory. All right, let's look at an example program. All right, so here's an example program. It's a relatively simple example, but you'll notice here in this program, we have int I equal 1. So we're creating an integer variable called I and setting it equal to the value of 1. So in the next line is just a printf that says the value of I is, and then %d is our format specifier that then this gets plugged into. So we're printing out the value of 1 right there because we haven't changed it. We haven't done anything with it. It's a value of 1. But then also I'm going to do a printf here. And I say the address of I is, and notice I'm using a %p. This was a kind of a decimal integer up here. %p is generally what the print format specifier for pointer values or addresses. So %p, it's p for pointer. If that is allows us to print an address. And then I put ampersand I over here. So notice the ampersand being used, ampersand I, the address of I. So with that address of I is now going to get displayed on the screen. So what does this do when we actually run it? Well, here's what the output would be. The value of I is 1, because that's what it's storing. But the address of I, where it is in memory, on my machine, when I ran this, I got this address here. Notice that's a fairly large number. That address, if I run that program again, it might give me a different address, because the program, when it runs, might be loaded into memory in a different place. That variable will get allocated in different places as a local variable, so it's being stored on the stack. So this address isn't always going to be the same every time you run this program. It might be, but it also might not be. And that's an important note. The address may change on different machines. So if you ran this program on your machine, you'd likely get a different address. It could be the same, but it's unlikely. If I ran it on my laptop, I might get a different address. If I ran it on a Linux box and compiled this and ran it, get a different address. It's just where in memory that variable is stored when we run this program. All right, so pointers, again, since every variable and every other piece of data and all code kind of live in memory, they all have an address. So everything about our program has an address associated with it. So, but one thing to note is we can't do this. We can't say change the address of I to be some other place in memory. So we can't magically make a variable change where it is in memory. We can get its address, but we can't change it. It kind of is where it is in memory. We can't just make it go somewhere else. Now, there is a way using typecasts you can access arbitrary locations in memory, which would be useful for certain system programming tasks. We have a piece of hardware that lives in memory. If you remember, we had those special I/O locations where things like the GPU live or the keyboard connects to. There are ways to access those things by specific address numbers. We're not going to look at that right now. We'll circle back to that later on. But right now, just think of, note that you can access the address of, get the address of really anything about your program. And you can store that in a pointer variable, which we'll look at in just a second. But we cannot change the addresses of where those things are. So that's why that's illegal. All right, pointer variables. A pointer variable gives us the ability to store those addresses in variables. So they are a special type of variable that's used to hold addresses. So in other words, if we can get the address using ampersand, it'd be nice to save that off in some part of our program. That's what a pointer variable allows us to do. So to create a pointer variable or declare one, we use int, we use the asterisk, and then the name of the variable. So this says PTR, that's not required. You can name it anything. You can say int asterisk I or Bob or George or X underscore 42. It's just the same. This is just a variable, just like I, J, K, X, score, gold, health, whatever. So that PTR has nothing to do with this being a pointer. What makes it a pointer variable is this asterisk here. And this int, we'll talk about that in a second. So essentially this is saying make a pointer variable that can hold the address, which is what pointer variables do, of integer data. So let's look at that a little more closely. So here's that line, int asterisk PTR. That's declaring that pointer variable. So that part is saying that the identifier that follows is going to be a pointer variable. So this is associated with that. The second thing, that's just the name of the variable, just like we would name any other variable. And the first part there says that's the type of data that this pointer is going to be the address of. And the reason that the pointer has a type is really kind of, there's several purposes for that. The first one is that makes sure that we don't misuse that pointer. In other words, we don't access it incorrectly or assign the wrong kind of data to it, the wrong address to it. So we don't want to put an address of floating point data into a character pointer, for example. Although C will allow us to do that. If we do typecasts, by default, the compiler will say, hey, you're trying to stick the wrong type of address into this pointer variable of a different type. So the pointer also tells the compiler how we'd like to interpret the data that at that address that's stored in that pointer variable. So in other words, once we have the address later on in our code, we might want to say, hey, go to that address and give me what data is there. And to know how to interpret that data, we need to know what kind of pointer it is. It has to have a type. So once we've created a pointer variable, we can store addresses in it and then use those in some way. So let's take a look at that. So here's an example. And notice that in this example, I create a pointer variable called PTR. I create an integer, and that's an integer pointer. I create an integer called J that's storing the value of 0. I've initialized it to 0. And then I also have this float variable X. And it's not initialized. And this is an important thing to note, is that when you create a variable, a local variable like this, and it's not initialized, and this is going to come up again and again. I'm going to kind of hammer on this because it's important, that C does not automatically initialize variables to 0. So when I say create a float variable X, that's going to allocate 4 bytes in memory somewhere to be X, to be that float X. But what's in there, if I don't initialize it, is going to be just random junk that happened to be in that space of memory. So again, C does not initialize the variables. When they're uninitialized, that means they're truly uninitialized. And notice the same thing is true for this pointer variable. I'm not initializing it, so right now it just has some garbage, whatever happened to be in that space of memory in there. Now, looking down here, PTR equal address of J, that's okay because I have an integer pointer. I'm putting an address of integer data into it. That'll compile just fine, no errors, no warnings. But if I tried to say PTR, which is designed to hold an address, and I tried to stick the address of a floating point value in there, even though the addresses are just addresses in memory, the compiler will say that that's the wrong type because we've said this is an integer pointer. Now, we could override that by casting that address as an integer pointer, and then the compiler would be fine with it. But the default is to warn us or give errors when we try to misuse one of those, try to misuse a pointer variable. In other words, giving it the address of a float when it's expecting or designed to hold an address, allocated to hold an address of an integer. Okay, so we can get the address of any piece of data that we want, any variable, and we can store that address in one of these special pointer variables. So what about going the opposite direction, or going the other way? In other words, can we get the data that's stored at an address if I just have the address? And obviously, if I'm asking the question, the answer is yes. So that's called dereferencing. So what pointer dereferencing is, it means that we want to get the data that's at some address. And in order to do that, we need another operator. And this is going to be what's called the dereferencing operator. It's kind of the opposite of the ampersand that we saw earlier. And I like to think of it as the thing pointed to by operator. And that's the way I read it when I look at code. Technical name for it is the dereferencing operator. But what we're really saying is give me the thing pointed to. Give me the data that's pointed to by this address. And that dereferencing operator is just an asterisk in front of some pointer variable, in front of something that's holding an address. So that says get the data item at this address that's stored in that pointer variable. So it'll probably make more sense if we go ahead and look at this example code here. So looking at the example code, we've got this int I equal 100, int pointer PTR. So we've made an integer I, it's storing the value 100. We now have an integer pointer that's storing the address of an integer. And now the next thing we do is we say point the pointer, set the pointer value to be the address of I. So we've put the address of this variable, where it lives in memory, into PTR. And now down here in my code, I say PTR points to %d, and I say asterisk PTR. So remember, that reads the thing pointed to. So we're saying, what's the data pointed to by PTR? Well, PTR had the address of I, so we go, where in memory is that? We go into memory and look at the data that's there, 100. And since that's an integer pointer, we interpret it as an integer, and we see that that's 100. So this is going to print out 100. PTR points to 100 when we actually run this. So even though we didn't use I here, we had the address of it. We said, give me what's at that address. What's at that address is the number 100. Now, one thing to note is that dereference operator uses the pointer type to interpret the data that's there. And we're going to see a lot of pointers this semester. And the reason for that is they're very important to understand, very important to C language, that they're kind of a critical part. And that makes sense because if you think back to how the computer works, it's a big bunch of memory cells that are storing data. Some of the data is floats, some is int, some is code, some is instructions, some is data for those instructions, some of it might be pixels. Well, if we want some programming language that can access that data in a really efficient way, it's useful to go into that data, know where it lives in memory, and then just access it. And as we're going to see later on, we're going to have the ability to move those pointers around, like up and down in memory, to go through, like we finished with this pixel, go to the next one, go to the next one, go to the next one. So we're going to have the ability to move those pointers from place to place, and we'll see that later on this semester. Okay, Moving on to operators. Before we get into that, expressions, there are 4 expression types in C: constant expressions, integer expressions, float expressions, pointer expressions. And really the only difference is a constant expression is one that only contains constant values. And those could be like character constants like that. That lowercase a, that's the same as if we put in 97. An integer constant like 10 could be a hexadecimal constant, an octal constant. It could also be things that are only have constant values, like if I said 10 times 5 or 0xff plus 17, those would all have constant components, so that's a constant expression. So even if I use operators there between the things, that's a constant expression. One thing about constant expressions is the compiler will go ahead and compute those values ahead of time and give you the result of that constant expression in the code. So even if I were to say like 10 times 5 and I wrote it that way in my code, the way it would get compiled is that those are all constants. The compiler will go ahead and compute 10 times 5 is 50, and it'll put 50 into your program for you. All right, integer expressions are ones that evaluate as an integer result. So here's an example here. We have this int j, that's definitely an integer, j plus 3, integer plus integer gives us an integer, j times j, integer times integer results in integer. So these two things here are integer expressions. Notice this doesn't really make a lot of sense. I'm not doing anything with those values, but just this is illustrating what integer expressions. Float expressions evaluate as a float or a double. And notice when I, rewinding just a little bit, when I talk about integer expressions, that can also include character. If I use characters in one of these expressions, it's still an integer expression. If I use long, those are still integer expressions. But note the distinction here is there is no fractional part of this. These, however, have a fractional part. These are floats. The last one is a pointer expression, which is why we covered pointers earlier, and that is anything that evaluates as an address. So anything that, so for example here, integer j, ampersand j, that evaluates as an address. One interesting thing that you may not have realized, when I put something in double quotes, that actually evaluates as an address too. And we'll see that again when we talk about strings in a few classes here. But notice this double quote hello, that just simply evaluates as the address of where in memory this string hello is. We'll come back to that later. So what expressions are, they always contain some kind of data items and maybe some operators that act upon that data. So you can see that up here. There's a variable times 2, that's an operator acting upon the data variable x and the variable 2. Okay, operators. All operators have a precedence level and an associativity related, or that is defined for them. And so the precedence level determines the order of operations. So you may be used to that from algebra or another programming language, like there's always that algebraic thing, PEMDAS, parentheses, exponentiation, multiplication and division, addition and subtraction. And you're probably familiar with that concept. You may be less familiar with the concept of associativity, but that determines when we have the same operator, like x plus y plus z, what order do we do those in? Do we do the x and the y first and then the z, or do we start at the end and work our way backwards? So with associativity, it's either going to be a left associative or right associative, or another way to think of it is it's either going to go left to right, it's going to go right to left. And you're probably used to, like, the normal algebraic order of operations is parentheses, exponentiation from left to right, multiplication and division from left to right, addition and subtraction from left to right. So you're used to that kind of left to right associativity. But let's go and look at the table, or the operator table for C. And this is a little bit small, so that's a little bit hard to see. But I did post, I'm going to post this to the course site so you can actually pull this up and look at it a little more carefully. Because I know if you're looking at this on your phone, it's going to be a little bit hard to see those. But you'll notice that there are essentially 15 levels of precedence. The highest precedence is at the top. The lowest is at the bottom. And at some levels, there are multiple operators at certain levels. So for example, at the topmost level, we have parentheses, but we also have plus, plus, and minus, minus. We also have this array subscripting up here. We have the dot operator, the arrow operator. We'll talk about those later on. But you'll notice that those are left to right, so the traditional associativity that you're used to. And then I'm not going to go over all these now. We're going to spend some time going over some of these. But notice all the way at the bottom is the least or the lowest precedence level, and that's the comma operator. So that one has the lowest precedence. Next up from that is the assignment operators. Next up from that is this ternary operator, logical or, logical and, bitwise or, bitwise and, or bitwise XOR, bitwise and, relational equal and not equal are in a group together. And so we're going to spend some time looking at these, but you'll notice that there are some operators as well. There's the addressive operator, and here's the dereference operator. Those are at level 2. And we've seen plus, plus, and minus, minus before. And in other languages, you've seen some of these arithmetic operators before that we see here. One thing that's notably missing from this is an exponentiation operator. Meaning raising something to the power. Notice there is this caret operator here, but that does not mean exponentiation. That's a bitwise XOR, so don't confuse those two. And we'll look at that, some of those operators here a little bit, and we're eventually in the next few classes going to touch on every one of these operators that you see here. All right, so let's look at a few of these operators in detail. All right, starting out with parentheses, just like you're used to, that's used for grouping, controlling precedence. So if I have something like this, y equal x plus 3 times 4, it's going to do the x plus 3 and then multiply by 4 because that has, as in the table, parentheses are all the way at precedence level number 1. The next one that we're going to look at is the unary positive and negative. So that's used for making a thing like -4, or you could do it with a variable like -x. Positive 10. Positive, the values default to positive anyway, but there might be a case where you want to represent a positive constant for some reason. You can still do that. And going back to our table, notice that the positive, plus and minus are at level 2 here, unary plus and minus. Those are not the same as addition and subtraction, which are down here at level 4. These have a higher level of precedence than that. Then we have the binary arithmetic operators. There are more binary operators that we're not going to look at today, but we're going to look at the arithmetic ones right now. So we have addition and subtraction. Then we have the multiplicative operators, multiply, asterisk, / for divide, and mod is percent. And as a reminder, mod gives you the remainder of an integer division. And I have a note down that says the modulus operator will only accept integers as operands. In other words, you can't put a float in either of the two positions on either side of the mod, or the compiler will not let it compile. Also note that there's no exponentiation operator, and there's a reason for that. Remember, C was designed to have this one-to-one relationship between the code that you write and the microprocessor's instruction set. A lot of microprocessors, or most microprocessors, don't have an exponentiation instruction. More modern processors have that, and like the math coprocessor for that, or the floating point unit. But traditionally, microprocessors did not have an exponentiation operator, so they left it out of C. So the way that you do exponentiation in C is by using a function in the math library called pow, which is a power function, which also exists in Python. But you call that power function, and it basically has an algorithm that just multiplies the thing by itself a certain number of times to compute that for you. But it's not included as an operator because there's not a one-to-one correlation between that and what every processor would do. And again, C being a systems programming language, it's designed to have that relationship, a very intimate relationship with the hardware that the code is being compiled to. All right, a few more operators here. We've got this assignment operator, which you're used to, just a single equal sign. Don't confuse that with a double equal sign, which is a comparison operator. We've talked about that a little bit in the last class. We have the modifying assignment operators. You're probably used to those from another language like Python, plus equal, minus equal. And oops, again, I'm going to fix that when I see it. That's the wrong description there. This is. So those are just modifying assignments. And then we have times equal, divided by equal, and mod equal. Those are also modifying assignments. So for example, x equals 0, and then x plus equal 1, x will then become 1. And then if I after that do x times equal 2, it'll double whatever was an x. So typical modifying assignment operators, these are the arithmetic ones. There are some other modifying assignment operators we'll look at later, but for right now, these are the ones that I want to focus on. Now, increment and decrement. Increment is similar to doing plus equal 1. Decrement is similar to doing minus equal 1. But there are two variants of that. For example, I could do the plus plus after the variable, or I could do the plus plus before the variable. Same thing with minus minus. So we're going to look at that in a little more detail here in just a second. But before that, notice that all assignment operators have right to left rather than left to right associativity. And the reason for that is because it allows us to do chains of assignment like this, I equal j equal k equals 0. And the reason that you can write code like this is essentially saying all in one statement, in one step, set I and j and k all equal to 0. And the reason that this can work is because it starts at the right over here. It sets k equal to 0 first, and then sets j equal to the result of that, which the result of any assignment is the value that was assigned. So j becomes 0, and then I becomes the value of that assignment, which was also 0. So in this case, I and j and k all get assigned to 0 simultaneously. So just note that the assignment operator works right to left rather than left to right, like you're used to with some other arithmetic operators. Now, we talked a little bit about increment and decrement and the two ways that that can be used. So let's take another quick look at that. So here, x plus plus and plus plus x. Now, both of those cause x to be increased by 1, like x plus equal 1 would do, but there is a difference. And the difference is, what do those evaluate as? In other words, if I were to look at what value this produced and assign that to some other variable or put it in a while loop, or an if statement, what value does that produce? And the difference is, this one, x plus plus, evaluates as x, but still increments x. So it's going to give us, when it's evaluated, it's going to give us the value before incrementation rather than afterwards. Plus plus x increments first and then gives us the value after it's been incremented. Now, if you look at that, that makes sense, because if we look at this one, the first thing we see looking from the left, well, do the left, is that first thing that we see is x. So this evaluates as x and then increments. Evaluate, then increment. This one increments and then gives us the value after it's been incremented. So this is kind of like the prefix version of it down here. This is the postfix version of it up here. All right, to make that make a little more sense, let's look at a quick example here. All right, so here's some example code. Here's an entire program. We start both I and j off at 5, and then we print out what I and j are, and then we increment I using plus plus I, print out the value, and then we increment j using j plus plus and print out the value, and then we print out I and j again. So this first print and the last one are the same. We're just printing what's in them. So both of them should go from 5 to 6. So they'll go from 5 to 6. So what's the output look like? Well, it's going to be 5 here for both I and j. So say I is 5, j is 5. And then at the end, it's going to say I is 6, j is 6. But here, when we evaluate plus plus I, remember that one is doing increment first and then give me the value. This one's giving me the value and then increment. So we're going to see a difference in what gets output here. So let's look at what the output is. So there's the output. I is 5, j is 5. Afterwards, they're both 6, but notice plus plus I gave us 6 because it increments and then evaluates, and j plus plus gave us 5 because it gave us the value and then it incremented after it evaluated that. And that can be important for using these incrementers in or decrementers in something like a while loop. So note that both have the same result, but they evaluate differently when we perform the incrementation, either plus plus or minus minus. And notice the precedence of plus plus and minus minus is also right to left, so backwards from the normal left to right that you're used to. All right, so one of the things about the precedence of plus, plus, and minus, minus, I want to look at that. And it allows you to do this increment operator and decrement operator allows us to do some strange things. So here in our code, we can say I plus plus, and since that evaluates as I before it's incremented, we can then use that, and here's a subtraction, minus minus j. So we have this weird code here that says I plus plus minus 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 j, and that will evaluate and compute just fine. But let's see if we can figure out what that's going to do here. So I, that's evaluating before it's incremented, so that's going to be 0, minus 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 j. So this is going to be a 0 here, and then we're subtracting from that minus minus j, but that's going to subtract first before it gives a value, so that's going to be 0. So we're going to say essentially 0 minus 0, we should get 0 from that first one. Now the next one, it's going to do I plus 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 j. Notice I reset the values of these, and there's that comma operator being used. So you could also put a semicolon here and it would work fine. We could not put a semicolon here and have it work fine. So this one is just a new assignment. This is a declaration and a initialization. So down here we reset them both to 0 and 1. So this one is going to be 0, evaluate as 0, and then we're adding to that plus plus j. So in this case, plus plus j is going to increment first. That's going to go to 2. And then the last one here, we're doing plus plus I plus j plus plus. That's going to increment this one first, get the value. So that's going to be 1 plus this is going to be 1. So that's also going to be 2. So what's the output? 0, 2, and 2. So take a closer look at those. Make sure that those make sense. The order of operations there. And one thing I would say is don't write code like that. If you want to have to do multiple things that have plus pluses or minus minuses with them, increments and decrements, and use that in some sort of arithmetic context, what I would do is rather than shoving it all together like this, maybe put parentheses around like this and that. And when possible, just avoid doing that kind of stuff altogether. Sometimes it can make for much more efficient code or slightly more efficient code, which couldn't matter in the case of something like a graphics driver or something like that. But for the most part, adding the parentheses certainly won't make it any less efficient. It'll just make it clear to whoever's looking at it. But if you have something like this, I plus plus minus 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 j plus minus minus k plus j plus plus, it just creates this ridiculous chain of things. It's going to be really hard for somebody, another program that follows you, to look at and understand what you're doing. So try not to do that unless there's a really compelling reason to do that. Okay, the comma operator we had mentioned. The comma operator basically evaluates one expression and then the next one. And we could see that being used actually back here. Basically perform one and then the next one. And notice that the order it goes in is it says evaluate A, then evaluate B, and the whole thing evaluates as whatever the last item was, whatever the last thing here. So this would evaluate as B. So over here, back in our example code, I equals 0, that performs that assignment, performs an assignment of j equal 1, and then that whole thing with the commas and everything was going to evaluate as 1, because that's what the last assignment evaluated as. All right, relational operators we saw before when we talked about decision statements, the if statement, the while loop, and those all produce either a 1 or a 0 as a result. And these three, notice, have a lower precedence than equal and not equal. But all of them, all 6 of these, produce either a 0 or a 1 as the result. So they produce a number as a result. 0 is false, 1 is true. Quick bug warning when using the equality operator and the not equal operator, these two here. If you're dealing with floating point values, any of these relational operators we have up here, it's important to be cautious when you're comparing floating point values using that. Now, why is that? Well, here's an example. We have 1 divided by 3, which is 1/3, plus 1/3 plus 1/3. So we have 1/3 plus 1/3 plus 1/3 should be equal to 1.0, but it's unlikely it's going to actually be equal to 1.0. And the reason for that is rounding error. Remember, the floating point values only have, If it's a single precision, we only have, what, 7.2 or whatever digits worth of precision. If we have a double, we've got like, what, 15 digits worth of precision. So when I say 1 divided by 3, I'm going to get 0.333333, some with 7 digits worth of 3s. And when I add that to that to that, I'm going to end up with 0.9999999, a bunch of 9s, which is not going to be equal to 1.0. So whenever you're comparing a floating point value, it's best to compare within some tolerance. So take the difference between that and the thing you're trying to compare it with and make sure the magnitude of that is below some tolerance. But doing a comparison like this can work on if you're comparing exactly with 0 on something, or some other values if you set it exactly to some value and then look at it later on, as long as it's representable. But just be really cautious when you're using double equal or not equal for comparing floating point values. Okay, a few things left here. The logical operators, just like the relational operators, produce either a 1 or a 0 as a result, and the precedence goes in this order. So this allows us to do not, and a logical not, a logical and a logical or. And since true and false are represented by 0 or non-zero or not 0, 0 is false, not 0 is considered true. If I say not, put the exclamation mark in front of some other value, essentially if it's non-zero, we get a 0. Otherwise, we get a 1. So if this is 0, we get a 1. If it's not 0, we get a 0. But the result is still always going to be 1 or a 0. 1 for true, 0 for false. So this inverts the logic of whatever followed it. And the logical and, both of them have to be non-zero to get a 1. So if this is not 0 and that's not 0, this produces a 1. If either one is 0, it produces a 0. The logical or, and this logical and is equivalent to like the word and in Python. This is equivalent to the word not in Python. This is equivalent to the word or in Python. But notice that we use these symbols for that meaning in C. Logical or, again, this is if that is non-zero or that is non-zero, we get a 1. Otherwise, we get a 0. So it works kind of as expected. The only thing that's different here is rather than in like Python what produces a true or false, it produces a 0 for false, a 1 for true. It produces an actual integer value. One quick bug warning, and I guarantee this is going to come up later on in the semester in some of your code, and that is don't confuse the bitwise operator single ampersand, single or, single vertical bar, or the tilde for the logical ones, which are double ampersand, double or double vertical bar, double pipe, whatever you want to call that symbol, and the exclamation mark. So if you use a single ampersand where you meant a double ampersand, it has a different effect. And we're going to look at these later on in the semester, the bitwise operators. And the bitwise operators are actually really cool because they give us direct access to the binary bit patterns that are stuff that is being stored, how things are being stored in memory, and they let us manipulate those bits individually, which again, C being a operating systems programming language or a systems programming language, that can be really useful. If you have some register where this bit has a certain meaning, you can use the bitwise operators to add a bit on or clear a bit off. And we're going to look at those later on in the semester, just not today. Okay, that's it for today. Make sure to look for the quiz that's going to be posted. And also make sure to look at lab number 2. And I'm going to post a separate video where I explain lab number 2 a little bit more carefully. I really miss being in class and being able to stand in front of a whiteboard to explain these things and have you ask questions. So once you take a look at the lab, look at the video that goes with that lab, ask me questions either by email or text message, or if we need to and you're confused, I can actually come in and we can go over the stuff in the classroom. Just make sure to contact me, communicate with me, and let me know. So that's it for today. I went through that stuff relatively quickly today, much more quickly than I would have if we were face-to-face. So if you need to, remember you can always watch multiple times. You can pause, you can rewind, you can pause the video, go to, remember there's that online, if you search for online C compiler, you'll find that online GDB thing. You can try out some of the examples that we had in there, see what happens. One thing though, when you take the quiz where it asks you to analyze and tell me what the output of a program is, I want you to think about that and try to analyze it yourself and type that in without leaving the quiz. So I may set up those quizzes so you can't leave that window without it submitting it. So just be aware of that. I want you to think through that stuff and learn that stuff. So make sure to look for the quiz and make sure to look for Lab 2 and get started on that. And that's it for today. Next class, we're going to continue on with some more things. And remember to communicate with me and let me know if you're having problems. That's it.